Hello, my smart and talented friends, and welcome to the Global Science Network. Today we're going to be testing whether we can make this RC Cybertruck a fully autonomous RC Cybertruck by controlling it with this artificial brain, which is an 8-neuron, hardware-based neural network. So do you think that with just 8 artificial neurons, we'll be able to autonomously control this truck? It seems like a hard feat, but we'll see if it's possible. Right here, this RC Cybertruck is being autonomously controlled by the artificial brain. What is cool is that you can actually see the brain activity that is able to drive the truck. I will explain how this spiky neural network works, and as you watch the full test video, you will understand exactly why all of these different neurons and synapses are firing. Now, since I built this on breadboards, the artificial brain is too big to fit on the truck. So the sensor data is sent to the brain, and then the brain circuit wirelessly sends the control commands to the truck. I am going to go into detail how this works and give you the full circuit diagram, neural network architecture diagram, and table explaining how to set the weights in the neural network. So this is going to be a completely open source project where if you want to, you can actually build this on your own. And I actually recommend just starting with building one artificial neuron, and then once you do that, build a couple artificial synapses, and then from there you can actually try and build your own network. Once you understand how it works, I will show you day 1 test results, which is basically where the truck was going full speed straight into the wall. So there were a few problems we had to solve. I will show how I was able to troubleshoot to solve the system delays. The day 2 testing results went much better, and I will show a full 2.5-minute clip of the truck driving autonomously. The RC truck is equipped with 4 proximity sensors to determine how far away it is from objects. That data is then wirelessly sent to the 8-neuron artificial brain to determine which way to turn and whether to go forward or backward. The brain is a spiky neural network where the neurons' change in firing rate determines the control commands. The firing rate of the neurons is determined by the inputs or synapses, which can be excitatory to increase the firing rate or inhibitory to decrease the firing rate. The output control commands are then wirelessly sent to the truck from the actual remote control, which I hacked so that the buttons can be controlled electronically rather than by pushing the buttons. Now, the reason this project is awesome is that the artificial brain actually works like our biological brains. I would say that this network is designed to be alive rather than to be a switch, which is the case for LLMs and AI projects that run on digital computers. This type of AI is called a spiky neural network. You can see that as the truck moves closer to an object, the firing rate of the neurons in that area of the brain increases. This is the same way the firing rate of the neurons in your actual brain changes as you think and interact with the world. The spiky neural network is more of an analog system where the network calculations are achieved by integrating trillions and trillions of charges, and these charges directly interact with each other in the system. This is very different than neural networks that are simulated on a digital computer, where each calculation is done in a discrete way without direct interaction with all of the other states. If you understand this, you can see that hardware-based neural networks have so much potential. In order for machines to achieve a high level of consciousness, they will need to be a neuromorphic, hardware-based neural network. In the How to Build Artificial Neurons video, I explained that even if you used every digital computer in the world, you still could not simulate and track the atoms in just one drop of water. The better method of computation is the spiking neural networks that can easily integrate trillions of states. Eventually, more people will realize this and understand the potential of hardware-based neural networks. I made a video about how artificial synapses work and how artificial neurons work. The goal of this project was to make a simple demonstration of how a small network of hardware-based neural networks could do something useful to show the basics of how this technology works. This is similar to the goal I had whenever I built a 4-bit computer using individual transistors on breadboards. Some people may have thought this computer is similar to the design of the Intel 4004 that was built in 1971. Some people even asked, why build such a basic computer? The reason is that the people who built this computer architecture in 1971 realized that all they needed to do was scale the project up and it was going to change the world. The idea is the same here. If we properly build a small network of artificial neurons, all we need to do is scale that up to create a much more powerful device. This design is a starting point. Once we refine it to be able to adjust the weights simply by interacting with the environment, then we can scale the project up and the results are likely going to be unbelievably awesome. These hardware-based neural networks should not require any software-based programming if built properly. The network should learn and be programmed simply by interacting with the environment. The initial physical structure of the network is the initial program. The program would then continuously be modified simply by interacting with the world. On YouTube, it is a bit challenging for a technical video to get as many views as entertaining videos, so I need your help to share this video. If YouTube shows this to 1,000 people, and all of you share it with one person who have not seen the video, after 23 share cycles, the video would only have 24,000 views. Now if everyone shares it with 2 people, that would be 3,000 views in the first cycle, then 7,000 views, then 15,000 views. After just 23 share cycles, over 16 billion people, which is more than everyone on the planet, would have got to see the video. That is the power of exponential growth, so remember that you are the ranking algorithm. This is why I am working to make content that is worth sharing. Not everybody is going to share the video, so if you could share it with more than 2 people, that would be great. Here's the full component level circuit diagram of the build. I called it the GSN SNN 4-8-24-2 Autonomous Vehicle. This stands for the Global Science Network Spiking Neural Network with 4 inputs, 8 neurons, 24 synapses, and 2 degree of freedom output. What is kind of cool about this design is you can control 1 degree of freedom, like playing Pong, with just 4 neurons. Driving a vehicle only requires 2 degrees of freedom, and this can be achieved with 8 neurons. You could even add a 3rd degree of freedom for up and down to control a drone with just 12 artificial neurons. With larger networks, you could add in more degrees of freedom and more features into the control logic. Here is the neural network architecture diagram. The first input layer is the 4 proximity sensors. The next layer is the artificial neurons that will fire at a rate based on the input of the IR proximity sensors. Each neuron in this layer connects to the neurons in the next layer with some weighted value. This means that it will send a large or small excitatory or inhibitory response to create the control logic based on these inputs. The output layer firing rate will determine if the vehicle is to go straight, turn right, or turn left, as well as whether to stop, go forward, or reverse. Stopping or going straight means that none of these neurons are active. Also note the added bias term to the forward neuron. When this is applied, the car will continuously move forward when the sensors show the path is clear. When the firing rate of the output of the neuron is above the threshold, it will activate the switch for right, left, forward, or reverse. How the weight should be set is shown in this table. For example, if the front sensor is activated, we want to send an inhibitory signal to forward to slow down. Having a high resistance connection to left basically does not change that value. Having a low resistance connection to right will make it so the vehicle will start turning right. The medium resistance connection to reverse increases the firing rate of reverse, but not enough to enable reverse. This is true for front, right, and left. This makes it so when all of these are activated, it will reverse the vehicle. When the back sensor is on, we do not want to reverse, so this is an inhibitory signal with low resistance. When right is on, we want to turn left, and when left is on, we want to turn right. You can look more at this table to understand the weighted connections. It was actually quite easy to set the network with these values. I was actually planning to have AI create a Python simulation of the network to determine the resistance values. For larger networks, this could prove useful, but the logic here was pretty straightforward, so it was not needed. Now let's look at the actual circuits. On the top of the vehicle, we have 4 infrared proximity sensors and circuit on 3 small breadboards. The output of these sensors goes directly into the ESP32 microcontroller, so the data can be sent wirelessly to the brain. The sensor data also goes into op-amps, which amplify the signal with a gain of 2. From the op-amp, the signal goes to an LED to display the activity of that sensor. There are 4 LEDs for the 4 sensors. The front sensor points straight forward and is called front. The left points forward into the left, the right points forward into the right. Finally, the back sensor points directly behind the vehicle. Now the main circuit has 16 full-size breadboards and is too large to fit on the RC truck. That is why we had to wirelessly send the data back and forth. In the future, we could build this on printed circuit boards to fit the artificial brain on the truck. Eventually, we could even use ICs to fit billions of artificial neurons on a small chip. Looking at the main circuit, we have the ESP32, which receives the IR sensor data. The output from the ESP32 is a PWM signal, which stands for Pulse Width Modulated Signal. The PWM signal goes through an RC low-pass filter to make it an analog signal. This signal then goes directly into an op-amp, which amplifies the signal, which goes into the first layer of neurons and to the display LED. The top 4 neurons fire based on the activity of these inputs. These neurons are called left, right, back, and front. The output of these neurons now contains very useful information for the next layer of neurons and is sent to each neuron in the next layer using 4 artificial synapses. These synapses will send excitatory signals to increase the firing rate of the next neuron or have an inhibitory response to make it less likely that neuron will fire. This basically means that the output of these synapses provide the weighted response for each weight connection in the neural network. The firing rate of the neurons in the output layer will determine if the vehicle will move forward, reverse, right, or left. In most cases, by default, the vehicle will be moving straight forward due to the addition of a bias on the forward neuron. The output of these neurons is also sent to another RC filter, which outputs an analog voltage. When the neurons fire rapidly, more than 4 or 5 times, the voltage goes above the threshold of 1.4 volts, and the bilateral analog switch will electronically press the forward, reverse, right turn, or left turn buttons on the remote control. This is the same remote control that came with the RC truck. I just hacked it by soldering wires to the push button switches. It took some reverse engineering to determine which pins needed to be soldered, as the control for this skid steer vehicle was not completely intuitive. Making it so we just electronically push the switches was easier than trying to send the exact output, as the pins could be floating, ground, or high. In the article I referenced in the description, I will provide more information about how this works. Basically though, each pin had 2 connections that were not used, and the other 2 were the ones that needed to be connected. Alright, now we want to see what happens whenever we place an object in front of the truck. So if we place it pretty close to the truck, obviously the front sensor is going to turn on. We can see that the front indicator light turns on. This signal gets sent into this op amp, which then goes into this artificial neuron. The artificial neuron here is modulating, and it's modulating at the same rate as these synapses here. So these are 4 artificial synapses, and then this information from these synapses gets sent to 1, 2, 3, 4, the next 4 neurons in the next layer. And whenever you have an object in front of the truck, what you want to do is you want to keep going forward, but you want to go forward a little bit slower, and you want to turn to the right. We just had to pick a default direction to turn. It could have been to the right or to the left, but we picked to the right, so we can see that the right neuron is modulating, and this switch here telling it to turn to the right is activating. If there's an object to the right, it's going to want to turn to the left. If there's an object to the left, it's going to want to turn to the right. And if there's an object straight behind us, we are going to want to just keep going straight forward. If there's an object blocking all 3 front sensors, we're going to want to go in reverse. And that's exactly what happens here. So there's an object to the right. Oh, we got to go left. There's an object to the left. We got to go right. Let's say there's an object to the front and to the right. We're going to still want to go to the left. If there's an object in front and to the left, we're going to want to go to the right. And that's exactly what happens. So what's cool about this is we can see how quick this happens. As soon as there's an object, it turns to the right. As soon as there's an object to the right, to the left. So this has got pretty quick response. I could hook it up to the scope and actually figure out exactly how many milliseconds the delay is. Maybe I'll do that in a little bit. This is fun. I like it. What happens if all 4 of them go on? It stops. That's what we want. Now the question is, does this truck have free will? Not really. If there's an object in front of it, that artificial neurons are going to fire. Now the question is, do humans work the same way? Do they have free will, or are they simply responding to their environment? It is debatable. People will argue it strongly both ways, but it's a cool thought. One thing I probably should have done is I probably should have had a small amount of current feeding into all of the neurons. So just by default, they were all just firing like once every few seconds instead of completely being off. The function would be pretty similar. Just having the neuron spike one time isn't going to activate any of these things. Even if you just go real quick, it's not actually enough to probably flip the switch because this threshold has to be reached, which is about 1.4 volts. So just a quick little burst like that, we could look at it on the scope, but it takes a couple fires before the switch will actually turn on. Something that I just noticed is that whenever there's an object in front, I did expect it to be turning to the right with this one modulating and the back to increase a little bit. But what I didn't expect, well, I also expected the front to slow down a little bit, but I didn't expect this left to be modulating at all. So it could be that I didn't have high enough resistance on the synapse going from the front to the left. So I could either increase that resistance, or we actually have 2 synapses here. So the synapse from this neuron is connected into this one. And if I make that an inhibitory synapse, it will make it so that if the right is activated, the left is not activated. And I'll make this one inhibitory as well. So if the left is activated, it won't activate the right. And we'll just double check our logic here. So if I put something in front of the right, it'll turn to the left. And if I put something in front to the left, it will turn to the right. I'll check that without this one here. Yep, so everything's working as expected. Another thing is by default, none of the sensors are on, but this truck is actually moving forward. This is the forward neuron modulating. We can actually flip this switch and that shuts it off. So if this is shut off and now let's say there's an object in front, we're actually going to turn to the right. And then if there's an object to the right, we're going to turn to the left. If there's an object to the left, we're going to turn to the right again. So this will actually make it so that it would actually orientate the truck in a way that there's nothing in front of it, so that then whenever we do hit this go forward button, it can start to go forward and not be directly in front of an obstacle. This is also kind of like consciousness, where you're turning it on, where yes, you have this being that exists, all the structures there, but there's not actually one neuron that's continuously going forward to say, yes, I'm alive. But you hit this little switch right here, and it's like, yes, now I'm alive. I'm just going to keep going forward and see what happens. It's kind of like a human, right? You have this consciousness, all of a sudden you're aware, you're moving forward, and as you interact with things, that's your life, that's who you are. Now let's look at the day one testing footage. The results were not great, but I did explain a lot of things about how this whole system works, and it is kind of funny to watch the truck crash. We are all set up. Hello, my smart and talented friends, and welcome to the Global Science Network. Today we have a really awesome project. What we have, so this Cybertruck actually has 4 proximity sensors, 1, 2, 3, and 4 on the top of the truck. And whenever this gets close to a wall, so let's move it away from the wall real quick, these LEDs on the top indicate whether one of these prox sensors is activated. So as we approach the wall from the front, we can see we're about 2.5 feet from the wall and we're already activating the sensor. And it's an analog signal, so as it gets closer to the wall, it gets brighter and brighter. And then you can see now we have the left prox sensor also activated. And now based on these being activated, the neurons in the artificial brain basically are going to modulate. So we can see that we have the front signal sent and we have the left signal sent. In this case, the truck would be moving forward and it would be turning right. And that control actually gets sent out by using this remote control. I'm going to do one test. This neuron right here is actually causing it to go forward all the time. I'm actually going to turn that off. So right now it would actually only be turning to the right. So I'm actually going to turn on this controller and see if it will turn to the right. Let's actually just do that and see what happens. And I was going to put a kill switch on this, but actually if I just turn the remote off, it should actually stop the car from moving. So right now, that truck is pointed at the wall, and it has the left prox sensor activated, which means it should turn to the right whenever I flip this remote control on. Let's see if it works. Okay. That was a little bit more than I was anticipating. Houston, we have a problem. I'm trying to think what the problem could be. So what I'm going to do is I'm going to walk on the right side of this, hitting the right prox sensor, and this should turn to the left. It might turn too much though. Yeah, it worked. That's what it was supposed to do. I'm not sure what happened the first time. So now if we walk in front of the left prox sensor, it should move to the right. And it did. Maybe it's overshooting a little bit. We're going to walk to the right. Yeah, sometimes it gets a little too much. A little too much oomph. That was good. We walk in front of this side. Yeah, there is a slight delay to it. All right. But yeah, this is working how I expected. Well, until that happened. To be honest, I'm not super happy with how it's going, but I'm kind of interested to see if it works when it's going full speed. So what we're going to do is we're going to turn on the go forward neuron. So now the go forward neuron is turned on, so this thing should go straight forward whenever I turn this on. This might wreck my truck right here, but you got to test it sometime. So let's see if it works. It did not turn. All right, I'm not sure why that didn't work, but we're going to try it again. All right, so we just ran into the wall, but it's supposed to be going in reverse. So I tried to troubleshoot it here, and what I did is I made it so that if the reverse is modulating basically faster than forward, then it should inhibit forward even more. So now it doesn't look like forward's on, so whenever we turn this on, hopefully it goes in reverse. Hey, it does. Hey, look at that. But let's see if our brain is doing what it's supposed to do. Right now it's up against the wall, so it's got front, right, and left on, which means it's supposed to be going in reverse. But it looks like forward is modulating faster than reverse. So we got to turn this so that it actually starts to turn on reverse. See, now it's going in reverse. So now forward is off, reverse is on, and we'll see if we get any better autonomous control. Luckily, it seems like this thing's a little bit more robust than I anticipated. So let's turn this on and it should go in reverse and then drive around the room autonomously. Well, that wasn't good. That's why we attach it with tape, so we don't wreck everything. Everything should be fine. I'm going to slowly bring it to the wall. Oops. Once it hits the wall, it should turn. Definitely fully autonomous. After day 1 of testing, I was happy to get some emotional support from some biological life that will love you even when your autonomous car test fails by crashing full speed straight into the wall. What do you guys think? What do you guys think, huh? You guys want to play with the RC car? Oh, you guys are scared? Oh, don't be scared. Who's that? Who's that guy? Oh, what's Rex doing? He's checking out the truck. Hi, buddy. You don't have to be scared. Oh. Hi, guys. Are you excited? Are you excited? Oh. His name's Raptor, because he's a velociraptor. Urgh. Now, who thinks we could make an AI, hardware-based neural network of Raptor? He chomps. The big takeaway from day 1 is that there was too much delay or that the car was just too fast. However, with minimal delay, the car should be able to go fast. Troubleshooting. Let's talk PWM signals. Whenever the signal gets sent from this RC truck to this other ESP32 board, it's done in a digital manner. So that digital signal, whenever it actually comes out of this ESP32 and goes into the neural network, it's actually what's called a PWM signal, which is pulse width modulated signal. So if you look right here, right now this is actually going into the front sensor. So whenever that's off, that's what the PWM signal looks like. So if we put an object in front of the sensor, we can see it changes the width of that signal. And now this width can actually vary based on the distance from the sensor. So if I go further away from the sensor, those pulses are going to get less wide, so basically more narrow. So that's further and further away, and then as I approach the signal, which is I'm doing right now, it gets wider and wider and wider and wider and wider all the way until I get really close. So even though these are actually a bunch of square waves, once we run it through a resistive capacitor filter, which is an RC filter, which is this resistor and this capacitor right here, that will actually turn into an analog wave, which is basically the average voltage of that high signal in the PWM signal. All right, now let's talk about the system delay. So what we'll do is we'll actually trigger this. So I'm going to put my hand in front of the right sensor. So now we have our response. Channel 1, which is the yellow line here, is actually hooked up to the output of this right proc sensor. Whenever we have something on the right side of the truck, we're supposed to turn left. So channel 2 is actually going to the output of the left command. So this purple line here shows when we're actually going to run through this whole network here and actually execute a turn left command. And if we look, there's 100 milliseconds per division. So that's 100, 200, 300, probably about 330 milliseconds before we actually say, okay, we want to turn to the left because there's an object on the right side of the truck. That's pretty slow. I would actually want that delay to be less than 100 milliseconds. So we have to go through and look at how we can minimize these delays. And I'll save this here so that I can pull it up on the screen and show you exactly what that looks like. So now we're going to look at where these delays are actually happening. Let's first find the delay to transmit the signal from this ESP32 to this ESP32. So we'll just hit single right here, and we'll put our hand here, and we'll see this is much faster. So this is way less than 100 milliseconds. So we can actually zoom out here. The delay is like 2.5 milliseconds only. If you look, that's 2 milliseconds. Less than 5 milliseconds. I'll save this. So that's actually a lot faster than I thought it would be. So these ESP32s are not the problem. I thought there was actually going to be like a 10 plus millisecond delay caused by that, but that's not the case. We'll try it one more time just to be sure. From the time I put my hand in front of the sensor to transmit that signal over to this breadboard, it's actually, it looks like about, this one was actually a little bit longer, about 7.5 milliseconds. That one actually was 10 milliseconds. I'm not quite sure why it was so fast the first time. We'll do it again. Yeah, that one's about 6 or 7 milliseconds delay. That one's 5 milliseconds delay. So the amount of time it takes to wirelessly transmit the signal from this ESP32 to this ESP32 is anywhere from 2 milliseconds to 10 milliseconds. And it's important to note that it actually passed through this RC filter where I'm measuring it here. So that means that this RC filter is also only a very small portion of the delay. All right, this one's very interesting. So it was the same thing. I applied voltage to the right sensor, and we're going to see how long it takes to go from the time it's received from the board to get through this artificial neuron, through this artificial neuron, and then start to send an output to that RC capacitor there. So what we notice is the yellow channel 1 is when the signal comes in, and you can see it actually steps up, steps up, steps up. So what happens is, if you notice, it's actually going to be flashing. So each time it's increasing in voltage, that was a flash. So that was basically 1 pulse, 2 pulse, 3 pulse, and we can see the voltage is climbing. But it actually has to get to the threshold voltage before it'll send the signal out. So if you look, it takes a few of those signals. The threshold is actually determined based on the input of this MOSFET transistor. So that input is around 1.4 volts. So this is actually 1 volt per division here. So it actually has to go all the way up to right about here. And this is, I think, 100 milliseconds per division. So that's 100, 200, 300, 400. So almost all of our delay is going to be in this capacitor charging up from these pulses. So if we would actually increase the frequency of this particular neuron right here so that it charged a lot faster, we would get much faster response. So that's something we're going to have to try. And real quick, I'll just show you how that worked. We'll actually hit single. I will put my hand here. And yeah, so that was actually about the same. So if we look, we're trying to get to about 1.4. That's 100, 200, 300, almost 400 milliseconds before we start hitting voltages of around 1.4 volts. All right, this screenshot is super interesting because it's actually telling us how long did it take for this to ramp up to the threshold. So channel 1 is on the one side of the RC filter, and the channel 2, which is the purple, is on the other side of the RC filter. And we can see that it actually takes about 250 milliseconds before it hits that threshold. And if we look, it looks like it's about 1, 2, 3, 4, about 4 pulses for it to actually reach the threshold, which is fine, but these pulses are about 100 millisecond intervals, which is about 10 hertz, and that's really slow. So if we actually were to increase that from 10 hertz to 100 hertz, and we were still using the same number of points to reach threshold, it would actually give us a 10 times faster response. So we're going to want to do something like that. Let's just test this again to make sure we get the same result. We're going to put our hand in front of the right sensor, and we can see we have 100, 200, only about 250 milliseconds to delay that time. We can see it took about 1 pulse, 2 pulse, 3 pulse, 4 pulses again. So it takes this left neuron 4 times for it to pulse before we actually reach the threshold to say, okay, we need to turn left. And again, that's fine, but the time between these pulses is too much. I was mostly going with a slow pulse rate because I thought it looked cool on the breadboard to kind of show that these are working just like our biological neurons and they're firing slow. But if I was actually firing these at like 100 hertz, it's just going to look like a solid light. You're not actually going to be able to see that they're flashing. But to get better performance, I'm going to have to do that for the next iteration. This is what our setup looked like. I couldn't zoom out this much to actually show you, but the car was sitting here. And the reason that the back light was on the entire time was because this car is facing the wall. So that's why there was lots of flashing during all that explanation. That was fun. It was cool to characterize all those delays. So what we have here is we have an input signal coming into this front neuron. And it looks like this neuron is just on all of the time, but that's actually not the case. It's actually just flashing at a really high rate. And that's because we swapped the value of this resistor and capacitor. So the resistor used to be 2K, now it's 1K. And more importantly, the capacitor used to be 47 microfarads, and now it's just 1 microfarads. So that's going to make it charge and discharge much faster. Well, how much faster? Let's take a look here. We're going to trigger our scope. And this is 1 millisecond per division. So it looks like it goes high and low in less than 1 millisecond, which means the max operating frequency is going to be over 1000 hertz, which is really good. And now when front's on, that's going to get sent to make it turn right. So I also changed the value of these ones over here. So let's swap and take a look at these values. We'll talk about them as soon as I get it hooked up here. So before we had values of 10K and 10 microfarads. Now we have values of 1K and 0.47 microfarads. So this is actually smaller than this one. This one was 1 microfarad. This one's 0.47 microfarads. I did that because I think you would actually get into a situation where the frequency might get divided in half if you had the exact same size capacitor. So I made it a little bit smaller, and let's check out what these values are. So we'll trigger our scope here. And this is still set at 1 millisecond per division. And you can see that it goes high and then low pretty much exactly in 1 millisecond, which means the max operating frequency of this one is exactly 1000 hertz, which is really good because now that signal going into our RC filter is going to be able to have a much faster response to hit the threshold. Before, it took like 300 or 400 milliseconds to hit that threshold. Well, now, hopefully that we're operating at 1000 hertz instead of 10 hertz, we're going to be able to hit that 100 times faster. So now we're going to adjust the value of the RC capacitor, and we'll talk about that next. So now I set the values of this resistor capacitor filter, and I used a 47 kilo ohm resistor and a 1 microfarad capacitor. And if we look, I think this is going to work out really nice. So right now we are at 5 milliseconds per division, and I set my trigger to go off at 1.4 volts, which is right where the threshold is for this MOSFET transistor. And if we look, the new delay is just about exactly 5 milliseconds. So we went from a 300 or 400 millisecond delay to what should be a 5 millisecond delay. And this should ramp up. It should take about 5 milliseconds to charge. That will trigger the switch to turn on. And it's probably about the same delay on the backside. So let's look at how many times the neuron fires before we hit the threshold. It looks like 1, 2, 3, 4 or 5 times. So if we get 4 or 5 pulses that are pretty close together, then this switch is going to turn on. All right, I just tested the system delay from entering the neural network up here just before the RC filter, maybe just after, but there's not much delay there, to the point where it hits the switch. Before that was 300 or 400 milliseconds, and now if we look, we're actually at 2 milliseconds per division, 1 millisecond per division. So 1, 2, 3, 4, 5, 6. About 6.2 milliseconds is our only delay. So again, if we go back to 1 millisecond per division, or 2 milliseconds per division, yeah, so 6.2. That's not too bad. So now I'm going to actually hook it up to the truck and see what the total delay is. But we know the delay from the actual Wi-Fi was anywhere between 2 and 10. So our total system delay now should be less than 20 milliseconds getting to the controller. Now the controller going to the truck and then the truck having the motors wind up might add a little bit more delay, but probably not too bad. We're probably sitting under 50 milliseconds. So this increases our chances of it working by a lot, and it'll be very interesting to test. All right, everybody, this is really good news. So I just tested the total system delay from the front sensor first receiving a signal to the car deciding that now it needs to turn right. And the entire system delay was actually, well, let's take a look. This is 10 milliseconds per division, so it looks like it's a little over 15 milliseconds. So we went from a 400 millisecond delay to now the entire system delay is only 16 milliseconds. So that is awesome. The firing rate of active biological neurons in the brain does vary, with the theoretical max being 1000 Hertz. During an active task, the average firing rate of engaged neurons is typically 10 to 30 Hertz. For motor neurons, it is typically 20 to 50 Hertz, with brief bursts up to 120 Hertz. These are not exact numbers, and for the sake of simplicity, let's just say that active biological neurons fire at 100 Hertz. Initially, during day 1 of testing, the artificial neurons were firing at 10 Hertz, which is 10 times slower than the response rate of a human. After increasing the firing rate to 1000 Hertz, the artificial neurons now respond 10 times faster than a human, and this could be increased further. The reason I was using a slow firing rate initially was I thought it looked cool being able to see the change in firing rates. The point of this project was to demonstrate how it works to market the idea. It took me a while to realize this, but sometimes marketing is even more important than engineering. Even if you have the best idea in the world and no one wants to help you bring it to reality, it is useless. In this case though, marketing ran us straight into the wall, literally, so let's focus on some better engineering. Now I will show clips from day 2 of testing, including test 16, where I will show a full 2.5 minute continuous test. Now I do have 2 cameras, so I might change the views, but it will be the full test footage. Day 2 of testing, we changed 2 main things. The first thing is we increased the distance in which these prox sensors will sense the wall, especially the front prox sensor. So the front prox sensor now is able to see the wall from way out in front. This is actually the front sensor right here, and it's actually already sensing the wall, even though it's about 5 feet away. And the second thing we did is we increased the firing rate. This made it so that our system delay went from being around 400 milliseconds of delay to about 12 milliseconds of delay. So now basically the response rate of this artificial brain is going to be 5 to 10 times better than I could do if I was manually pushing the buttons on this controller whenever I saw that the sensor was engaged. So I think that we have a lot better chance of having this work today. So let's test it out. And let's test it. Look at that. It's not hitting the walls. It's supposed to be going forward. I think the battery just died in the vehicle. I didn't charge the battery. Day 2, test number 16. I'm going to flip this switch and then I'm going to go to the back left corner. Oh, it turned this time. Everything's going good. It's like a rodeo. Oh, it's like a barrel racer. Oh, it's doing great. Oh no, I didn't avoid that one. It's doing awesome. This is incredible. Uh-oh. There we go. Good boy. This is the best test yet. Oh, it hit the obstacle. Yeah, it's still working. Uh-oh. It does not like this yellow one. And it died. Look at that. That was the best test yet by a lot. Good job. Car battery died. It hit the yellow a couple times for some reason, but all in all, that was very impressive. I hope it was recording over here. All right, good deal. Almost 3 minutes of autonomous control. We will call that a success, and that might be the final test of this particular configuration. I'm going to change this so that it works and it will have full analog control instead of just going full speed or full right and full left. But way to go. This truck did it. It's awesome. Here I am showing the circuit close up. This will help you see how everything is wired. I will talk briefly about each part. At the top, you can see the RC filters and op amps. Next is the first row of artificial neurons. You can see how the synapses and neurons are wired. One change I made from the How to Build Artificial Neurons video is that I added a switch so that each synapse could change to be excitatory or inhibitory depending on the position of the switch. This makes the design much more flexible. To see the values of these components, I recommend using the circuit diagram. If you email me, I should be able to send you the circuit diagram. The second row of neurons only has 2 synapses per neuron. This row also includes RC filters and op amps. These ICs are the electronic switches. Links to most of these parts are in the video description. Here is the 5-volt battery pack, which is used to power the primary circuit. Finally, here is the RC truck remote control, which is powered separately with 2 AA batteries. All right, you might wonder, how am I going to install these sensors on this truck? And I'm just going to do it with some double-sided tape. We can see we got the battery in here. That's where it's going to sit. This is a 4.8 volt nickel cadmium battery. And if we look at the back of these sensors, the breadboards with the sticky tape, I just left this on. It doesn't stick very well to the double-sided tape, but the metal sticks really well to the double-sided tape. And I just did the front one because I don't want it to stick too much, because I want to be able to get the battery in and out. So all I'm going to do is take this and set it on top of the truck. Now we just have to connect this battery terminal. All I did is twisted some wires together, and it's going to fit right in that junction there to plug that in. You do need to upload code to tell the microcontrollers which channels will be used to transmit and receive the data. I had Claude help write the code, which I then uploaded from the Arduino IDE. AI wrote the code and it worked on the first try, which was fantastic. In the video description, I reference an article with more information about this project where I share the code and provide further instructions. After day 1 of testing, my brain would not shut down trying to figure out the issues. In addition to solving the delay, the other part of the solution was to have full analog control, so the vehicle can travel slow or fast depending on the sensor data. I even almost immediately started building a robot and made the new design. This design will be able to directly access the motors with the L298N motor driver module. It will almost be a plug-and-play setup for the robot or RC Cybertruck, so that will be coming soon in an upcoming video. I already made the thumbnail, so I pretty much have to make the video. I was about to make that change for this video when I realized that just minimizing the delay would probably make the RC truck work, and I was very happy that was the case. To watch the next video, click here.